Hi, this is Professor David Farina. In today's lecture, we're going to be discussing the terrestrial planets, in particular the orbital and physical properties and the rotation rates of these Earth-like worlds. Let's get started. So to get us started, let's talk about the orbits from this top-down perspective. As you can see with the Sun in the center, a heliocentric viewpoint where we can see the closest planet to the Sun is the planet Mercury. It has the shortest and smallest of the orbits of all of these worlds. Can only be seen about 28 degrees away from the Sun at any particular point in time. The next planet, Venus, is in the second position from the Sun, and the maximum that Venus can be seen from the Sun is 47 degrees from the Sun's point in the sky. What does this mean? Well, first off, the reason for this effect is because the planet Mercury and the planet Venus are inferior planets. It's not that they are in any way less than the Earth. It has to do with their orbits. So by saying they're inferior planets, we mean that their orbits are smaller than the Earth, and therefore they're always seen next to the Sun in the sky. The result of this is that you're often going to see these two planets in the morning or the evening sky, either right before sunrise or right after sunset. And this has to do with the fact that when they're close to the Sun, you're going to always see them right around that morning or evening time period. They are, however, in the sky throughout the day as well. The problem is that the Sun is so bright that they're very difficult to find. If you know where they are, though, you can actually look through a telescope at the planet of Venus in broad daylight. It's kind of an interesting concept. You need to be careful, of course, when looking through a telescope anywhere near the Sun. So you want to do this when the planet Venus or the planet Mercury are as far away from the Sun as they could be in order to do that type of telescopic observation. Mars, on the other hand, is a superior planet to the Earth, and that means that it has an orbit outside of the Earth's orbit. And as a result, Mars can be seen both day or night, and that all depends on where Mars is in its orbit throughout its time around the Sun. In terms of other physical properties of the terrestrial planets, you can take a look at each of these on the data table above. I'm going to let you pause the video and look over the data table now. Now that you've had a moment to look over the data table, you might want to start looking at how we discuss the terrestrial planets. Oftentimes, we are going to use the Earth as our comparative planetology. In other words, the planet Mercury is 0.055 Earth in terms of its mass. It is going to be 0.38 in terms of its diameter across. It's going to have the surface gravity of approximately 0.38 Earths. It's going to have 4.2 kilometers per second of escape speed. And when compared to Earth, that's about 11. So this one is not compared to Earth, but you can make that comparison. The escape velocity or escape speed has to do with how fast it takes to get off the planet with a rocket. So on Earth, that's of course more because we have a higher gravitational potential. And these numbers here are going to coincide with those two things. Surface rotation period is how many days. Well, of course, Earth is 1.00. Earth is the standard here. So in Earth days, how long does it take to go around? In terms of surface temperature, these are in Kelvin. Remember, that's starting the scale of absolute zero, where zero is the lack of molecular motion, the vibration of particles or atoms within a substance would be the 0 point, absolute zero. And in terms of atmospheric pressure, once again, we're using the Earth as our standard. So you can see a planet like Venus, for instance, has 90 times the surface pressure of Earth. So in terms of rotational rates, Mercury can be very difficult to image because of its size, its proximity to the sun, but we can actually measure its surface rotation from using radar and a Doppler effect, as we've discussed in previous videos. So we look for the red shifts and blue shifts of the light coming from this object in the radio spectrum. Now, one of the weird things that has to do with the fact that Mercury is very close to the sun, it's also a very small body, is that we, for many years, thought that Mercury was tidally locked to the sun, in that one side would only face the sun at any given time. We now know that that is not the case. In 1965, that was proven to be false. We have now determined that the planet Mercury is in a 3-to-2 resonant frequency. So in other words, Mercury is going to rotate 3 times for every 2 times it orbits. Okay? So there are 3 days on Mercury for every 2 of its years. I'm going to say that again. There are 3 Mercury days for every 2 Mercury years. It's kind of a weird concept to consider. Now, if you look at this diagram, you'll notice that all of the planets are going around the sun in the same direction, counterclockwise from the top-down view. The rotational rates and directions of all of the planets, except for Venus, are also all counterclockwise. Venus is, however, going clockwise from the top-down view. And in terms of the words that we use in astronomy, instead of using clockwise and counterclockwise, we use the terms prograde and retrograde. So all of the planets are going prograde around in their rotations, with the exception of Venus, which is going opposite, or retrograde. Thanks for watching our video today on the terrestrial planets, orbital and physical properties, and rotation rates. If you like this video, please click that like button. If you would like to learn more, please hit the subscribe button. And if you'd like to get a notification each time I make a video, please ring that bell at the bottom. Thanks a lot, and have a great rest of your day.